Look, thanks very much, everybody, for coming along. You all know me, at least people in this room all know me, and I can't see who's online at the moment. And what I thought I would do in this sort of supplement to the main lecture I gave last Thursday is just give a bit of an overview of some of the other things I've been working on over the last little while. Not everybody could go to last week's talk, so for those who missed it, I was talking about alpine fault science generally, and I did make reference to some of the work I'll speak about today, which is this new field of distributed acoustic sensing. But the focus today is really on this new technology. And not least because I've now given 17 or 18 lectures, this is going to be a pretty informal once over lightly about what I did in my holidays type thing. But what I'd like to just bring you up to speed on is some of the work that I and others in this group and elsewhere in the country and overseas have been doing using distributed acoustic sensing in New Zealand over the last couple of years or so. And I'll introduce the technique, say something about why it's an exciting new way of recording signals emanating from the Earth, and then talk about some of the projects we're working on. Just to give you an explanation for this opening figure, this is an aerial photograph of an area just southeast of Haast in southwestland, where the main highway, which is the grey line, it's a little bit hard to see the grey line, but it's running diagonally across the slide here. The grey line runs up from Haast to Makarora and Central Otago, and Chorus have installed an optical fibre cable along that highway, which is the purple line. And at this particular location, the two of them cross the alpine fault. And so, in a sense, that's a bit of a shame for the infrastructure, but it provides a real opportunity for us to make useful measurements. So, this field of distributed acoustic sensing is something that's changing, as I'll show in a second, extremely rapidly. And you might think of it as just one particular method of what's now being called photonic seismology, using basically cables transmitting light to detect ground motion and vibrations. And these cables might be, as in most of the studies I'm talking about here, they might just be cables installed for broadband telecommunications purposes across the country, or they might be something that you've put out temporarily for a dedicated field study, or increasingly they might be the transoceanic cables that span thousands, tens of thousands of kilometres and can be used for some very novel measurements. Distributed acoustic sensing, that I'll be focusing on today, is just one of these new methodologies. And in particular, it's typically being used these days with telecommunications cables, repurposing them as very closely spaced seismic sensors that we sample with very high sampling rates, typically hundreds of hertz or kilohertz, and spatial sampling of the order of meters. So this is really is an expanding field, and I'll show you in a second how quickly things are developing. This is a sort of tricky slide. I've actually extracted this from a lecture I gave to the fourth year students a few days ago, but I just wanted to introduce some of the key components of what I'm talking about, and then we'll go through them in detail. The basic process of making distributed acoustic sensing measurements is to take a long glass fibre, and in a typical terrestrial telecommunications cable there might be dozens of such fibres. Take one of those fibres and fire pulses of laser light down it. And if you just focus on the top left-hand figure for a second, we send a laser pulse down a fibre, and most of it makes its way to the other end, and that's what's used to transmit the internet, TikTok, Instagram, whatever you like. But along the length of that fibre, there are optical imperfections in the glass at the atomic scale. And they're illustrated in this figure by the little green and blue dots. These are just, atomic scale imperfections which, when they are illuminated by a laser pulse, scatter the light, the incident light, and they scatter it in all directions via a process known as Rayleigh scattering. Now, some of that light is scattered back towards the source of the laser, and we can record it. We can basically send a pulse of laser light and then record what is scattered back to us. So in a sense, we are able to make a measurement by putting a laser at one end. We don't have to have anything at the far end. We're just looking at the naturally scattered light. And then we send another pulse a fraction of a second later, and we do the same thing. We look at what comes back, and we compare the phase of the light that's scattered back to us. Now, how that's done in practice is that we take a cable like this one illustrated in the top right. It's just a regular telecommunications cable, and it's probably worth emphasizing that it hasn't had anything special done to it. It doesn't have sort of gratings etched into it or any other sort of structure to it. It's just the cable that's used for your internet. And we attach onto the end of it a laser device, which is typically about the same size as a desktop PC, and we fire the laser pulses down there. What we are measuring is, as a function of distance along the cable and as a function of time, is the strain rate of each portion of the cable. So if you imagine a cable sitting in the ground, as it sits there, maybe a car goes by, maybe someone walks over the top of it, maybe an earthquake happens or there's an avalanche or something, it vibrates a little portion of the cable, and by comparing the light that's scattered from one pulse with the light that's scattered from the next, we can infer the strain rate as a function, as I said, of distance along that cable and time. Now, in practice, we are using, as I said, kilohertz or many hundreds of hertz type sampling frequencies. So that means we're sending a pulse every millisecond or so. We have to wait till the light from that pulse has been fully scattered back to us, so we can't sort of record to the edge of the Earth. We have to, start recording after a certain time and then fire the next pulse. And we're also making measurements on the scale of what's called the gauge length. And the gauge length is governed by the laser that's being used and by the optical properties of the fibre. And for the measurements I'm talking about, it's typically of the order of several meters. So this really is a field that's expanding sort of beyond sight. This is a picture that I quite like, and I've always thought of it as being an up-to-the-minute snapshot of what's happening. But actually, when I thought about it, this is pre-COVID. It's 2019. And a colleague at Caltech, Zhong Wenjian, published a paper in which he just drew attention to the rate then, in 2019, at which publications on DAS, which are shown in the blue bars, were increasing. Of those, a small fraction, really only starting about 10 years ago, were in geophysics. And the proportion of the total number that were in geoscience was of the order of 10 or 15% in 2019. There's been some really amazing studies conducted since then, and just as one example, I show this picture on the right-hand side, which, even to those of you not used to looking at seismic data, you might recognize this as a collection of seismograms recorded at different distances around the world from an earthquake happening at distance 0. These are different distances around the Earth's surface, and the seismograms plotted here are spanning an hour, I think. Now, the difference between this diagram and most you'll have seen previously is that each one of these seismograms is actually coming from a distributed acoustic sensing array, from a DAS setup. And the records shown here are from the very devastating February 2023 Kahramanmaraş earthquake in Turkey. So that happened a couple of years ago, and was the first time that DAS researchers around the world had really come together to record over the course of a month data sets from all the different corners of the Earth to look at what could be done. So I just put a figure together a few days ago. I did it mostly for my own purposes, just to look at how the number of papers in earth sciences and DAS are increasing year on year. Obviously, 2025 is not yet completed, so there's a drop-off at the end, but you can see that it really is increasing very rapidly. And it's driven by advances in computing power. You really do need a lot of storage capacity and a lot of computing power to do this sort of work, and it's being driven by increasing opportunities to use cables that have been put in by telecommunications companies for their own purposes. So we're basically, to put it bluntly, we're freeloading on the cables that have been installed to deliver internet connectivity, and we could do so in a way that doesn't get in their way, it doesn't interfere with things. And the main reason for that is if you took a cable and sliced through it, which occasionally happens, you would find that it's got, as I said, dozens of fibres. And in a place like the West Coast, which I'll be talking about shortly, they really only need 2 or 3 of those fibres to transmit as much TikTok as anyone wants to watch. So there's plenty of spare capacity for the sort of measurement I'm talking about today. So to give you an idea of what we get out of this sort of system, imagine a cable. I'll be talking about cables which are tens of kilometres long, at least the bits we're using, and the cable might be tens of kilometres long, but we are sampling it every 4 meters, for example. So between here and the window, there are 3 or 4 measurement points, and at each one we're recording a seismic wiggle as if we had a geophone or a seismometer placed in the ground every 4 meters. So this is just a simple comparison of the record from a seismometer up the top with one channel from a DAS system, one 4-meter spaced virtual sampling point. So I'll talk about this more in regards to our experiments later, but we're dealing with thousands of channels spaced meters apart, and so we get very, very dense records. And it's incredible that you can take just one of them, extract that, and have a record so similar to what's recorded traditionally. The picture down the bottom, these are called spectrograms. They're showing the distribution of energy at different frequencies as a function of time. For experts, that might be important, but for the rest of us, the thing to take from this is that DAS systems, particularly when we start averaging adjacent channels, if we want more signal to noise, we just average the channels because we've got so many, and we can come up with pictures of earthquakes in this case that look incredibly similar to what you get from a traditional sensor. So in terms of where I want to take us from here, I'd just like to go back about a decade to what we first did in the Alpine Fault borehole. This was actually quite ahead of its time in many regards. We installed a fibre in the cable in the borehole. We made measurements of temperature using a similar but slightly different technique from what I'm talking about today. And we also made measurements of earthquakes and active sources shots. That's 10 years ago. Since that time, I've been involved in projects focused on Haast and Milford Sound, which I'll spend quite a bit of time on. I'd like to just tell you how we do it, so you can see, in a sense, how easy it is, but how fortunate we are to have companies that own these cables who are prepared to give us access. We are currently acquiring data across Cook Strait. We are recording, and this is work led by Richard Callett at Earth Sciences New Zealand. We're recording on a 60-kilometre length at 10-metre spacing right now. And we've got some upcoming experiments which I'll talk about briefly. The diagram that just played was just sort of meant to blow your mind a little bit and show you what happens, in this case, if you have about 25 kilometres of fibre, each one recording at a great rate of knots, and an earthquake occurs. And I won't replay it now, but you might have seen the waves come across. And now in this static image, we can see the P wave, clear P wave and a clear S wave. I will mention that the volume of data is sort of overwhelming. In the time that this slide has been up, we've probably recorded a couple of gigabytes of data, and we recorded of the order of a terabyte per day. So that does pose problems for putting this sort of technique into operational use. But I won't spend too much time on it today. So like I said, we started about 10 years ago in the DF2P2B borehole. I mentioned this in the main talk last week. We have a fibre that runs from the surface down to about 819 metres. Due to some traumatic events, which I won't cover now, we don't have access, we don't have physical access to the borehole below 400 metres now. But the 400 or so metres below that still has the fibre running to the bottom. And we've been able to make measurements, as I said, at the time the fibre was installed and shortly afterwards, and we've been back a couple of times since. When the cable was last checked, which was 3 years ago now, the fibre was still intact and usable, although it was degrading. And the reason it's degrading, as I alluded to the other day in my main talk, is that this is an extremely hot borehole. And at the bottom, the temperatures exceed 100 degrees. And so the fibre has been sitting there cooking, and it really wasn't intended to be installed under such high temperature conditions. But that's where we were. We were mostly recording active source shots. We also did record some earthquakes, and we recorded some ambient noise just over the space of a night or two. And we were able to compare the DAS records, as is shown in this figure here, which extend to the bottom of the borehole, with more conventional measurements made using a vertical seismic profiling string, a VSP string. Those measurements were made in the top 400 metres, and they marry up very well with the DAS. Anyway, that's what triggered it all. What has occupied perhaps more of my time recently is the work we've been doing down south, and this is work that's been a really fantastic collaboration with Megan Miller and her group at Australian National University, and Stefan Hamerling and his group in the Technical University of Dortmund. In this particular case, we gained access to Chorus's fibre, which runs down the coast from Fox Glacier, gets to the Haast River, it crosses that, and at the Haast Aerodrome, which is marked by the big black circle, there is a junction box, and that is part of the telecommunications infrastructure that provides all the local connections to the people of Haast. And then the fibre continues along the highway, heading in a southeast direction across the fault and up towards the Haast Pass. We approached Chorus and said we thought there was an opportunity here to use some of the dark strands of glass, that is the fibre strands without data in them. And despite their initial surprise, I suppose, we prevailed and they were very happy to support us. And it's been a fantastic relationship. They saw it as a useful opportunity to showcase science and infrastructure being used together. And we were able to do it with very few obstacles. So to summarise, broadly speaking, what we did, we put our interrogator, our laser system, this big white box here, which we've imported from Australia. We put it in the Haast Aerodrome shelter, and then we acquired a short amount of data heading north on the north line and a lot more data on the southeastern line or southern line. In total, we recorded about 6 months of data on the southern line, which has since been analysed by several master's students at this university, a PhD student in Germany, and several postdocs, so it's been really valuable. This is what it looks like, a little bit boring, I guess, but I just wanted to sort of show you, first of all, a picture of what it looks like. This is on the floor of that little hut. That little hut is shown in the top right on a typical Haast day. We have something which looks like a PC, but that's actually the laser in there. It's a very big laser, and it has internally a lot of optical recording equipment. It's connected to another black box, which is a NAS data storage that has a capacity of many, many terabytes. And this big thing here is just a modem that enabled us to, or a router that enabled us to connect to the system in some of the later phases and control it as if we were sitting right there. So in this diagram, which is basically just a wiring diagram, I'm showing in orange the pieces of equipment that are operated by Chorus, and in particular the fibre under test, FUT, that extends out of the hut and heads up towards Wanaka, for example. They have their optical switching and optical connection equipment there, and then we brought along all the blue things. And it was easy to set up. Basically, when it comes down to it, you need to plug all your equipment into some power, and you need to take a fibre out of their system and connect it into the laser, and then away you go. So I think I mentioned this sort of thing on Thursday, but not everyone was there, so I'll just mention it again. We acquire huge volumes of data, as I mentioned, and we are sensitive to anything that's causing the fibre to vibrate. So I'm particularly perversely interested in earthquakes. So here's a nice record of an earthquake, a magnitude 4.5 earthquake, somewhere not too far away, recorded on about half of the cable. You can see a very nice transition from the pre-event clear record, nothing happening, to a P wave, to an S wave, and there are other features in there which are of interest as well, which I might talk about later. But in addition to that, we have traffic noise, for example. Each one of these lines is a car traveling along the highway, and cars are the most obvious, or vehicles are the most obvious, but we can also detect things like people walking along the fibre. We can detect horses, and I'll show you some examples later of some slightly more macabre things. But basically, if you were interested in this from the point of view of roading operations, you could use this to measure vehicle speeds just by putting a ruler on it, effectively, measuring their velocities. You can look at the weights, or at least the effects on the cable, of each vehicle, and you could probably say something about the number of trucks versus the number of cars, etc. You can look at things at the time of day, how much traffic is there heading towards Haast or away from Haast in the afternoon or something like that. So by recording so much data, we are able to split it up for different groups of users, and not so much at Haast, but at Milford Sound, which I'll refer to later, the roading operators are very interested in what I consider to be byproduct. So I mentioned this talk the other day, this network the other day. This is something that's been running or was running for a couple of years, the Southern Alps Long Skinny Array. And this is a network not of distributed acoustic sensing sensors, but just of regular seismometers deployed with what we thought was pretty impressive spacing, about 10 kilometers on average, between Milford Sound, or just south of Milford Sound, all the way up to Springs Junction, Maruia, at the northern end. And the point of mentioning this here is to say that this was the first time that we'd had a network that was operating along the entire Alpine Fault all at once, and so it gave us a really impressive volume of data that we could use to do a whole bunch of different studies, some of which have been led by people in this room like Carmen and Olivia and others. But this area down here is Haast, and so you can sort of see that there were quite a few SALSA networks, SALSA instruments operating near Haast. In general, the array was very skinny. It was sort of 1 seismometer wide, but near Haast we have a bit more, it's a bit more extensive. And so while that was out, we decided to collect the DAS data set. Now, here are some other earthquakes recorded by the DAS cable. This, I don't know why I do this, but in this case, distance is along the horizontal axis and time starts at the top and goes down. Hopefully you can see here too a nice clear P wave arrival, followed a second or two later by an S wave arrival. And there is structure in both of those, which I won't go into here, but one of our other master students, Alan Raudzep, has been looking at. And the point I want to make here is that it's all very well if I take a student and say, right, can you pick the time that a P wave arrived at this seismometer or an S wave, or maybe do it for the whole network. That's sort of tractable. But when you have 25 or 30 kilometers of fibre and you sampled every 4 meters, even I wouldn't ask a graduate student to pick them all. And so what we had to do is look at ways of using artificial intelligence, machine learning type techniques to do the picking for us. I mean, it's pretty obvious where the different waves are, but to actually make those measurements and spit them out in a coherent way is quite tricky. So a student of ours, of Callum's and mine, Isabella Silveran, has done a master's degree focused on this. And the basic challenge is to take a slice of data, which might look like that, but there's another smaller one there, run it through a convolutional neural network, and spit out your best estimates of where the P wave arrival is and where the S wave arrival is at each one of 7,500 locations. And when you do that, for this particular slice of data, you can overlay the forecasts out or the predictions, and this is where the P wave is, the green line, and this is where the S wave is. And there's some inconsistencies, partly related to the structure I mentioned earlier, and when you get over to the right-hand side here, the system obviously is going to be confused because you get lost in the noise. But anyway, that's the sort of technique that Isabella explored so that we could take this enormous volume of data and pull out earthquakes, both those we knew about because GeoNet had told us, but also those that we didn't know about and we wanted to search for. So this is a complicated diagram, and I'll just spend a second to explain what it is, but really the key thing to notice is that this is a time series. It's a record spanning a couple of months, showing in the blue symbols the detections we made by running all of those DAS measurements through this convolutional neural network to detect earthquakes. And what we've done here is we've linked each earthquake that we detected, each blue dot, to a red dot, which is an earthquake that we recorded separately using the SALSA network. So SALSA, I'm very proud of it. It's very sophisticated in certain ways, but for our purposes, we're using it as a ground truth, because in the vicinity of Haast, it can detect most earthquakes down perhaps to about a magnitude of 1. And so the way we are doing this comparison is saying, which of the events that we detected can we see in the SALSA catalogue? And the SALSA earthquakes here are plotted on a scale on the right-hand side, which is in seismic energy density units. Seismic energy density is a way of incorporating in one number the effects of distance and magnitude. So it's a function of distance and magnitude, and basically if it has a high seismic energy density, we'd expect it to be a big wiggle on seismic record, and if it's a low seismic energy density, either because it's a small earthquake or because it's far away, or for both reasons, then that'll be very hard to see in a trace. So this is what happens if we run 2 months of data through, we make a whole bunch of picks, and we think about the sizes of the earthquakes that they correspond to using our SALSA records. The picture on the right shows all the detections from both networks, and it's too busy to be of much help. But the point is that these are different networks, they have different sensitivities, and that is actually one of the areas of current research to figure out what DAS is sensitive to and what it's not sensitive to. So Isabella, as part of her study, she looked at this in some detail, and she said, right, I want to know which earthquakes recorded by SALSA can we also see in this much, much larger DAS data set, and which can we not? And so on this diagram, she's plotted as coordinates magnitude and distance. She's plotted the earthquakes of greenish color that were recorded by SALSA, but which we cannot see in the DAS data, despite having thousands of channels. And then in the yellow dots, it's the earthquakes recorded by SALSA that we can see. She's done the same thing for GeoNet with the green symbols and the purple symbols. The challenge of using GeoNet in this particular part of the world is that the network spacing is quite coarse, the magnitude of completeness is quite high, which means it's not detecting lots of small earthquakes. And so the comparison between the DAS and GeoNet was a bit less revealing, I suppose. But you could probably squint at this for a while and realize that you could put on a line that separates SALSA events, for example, that we mostly don't detect from those that we mostly do detect. And that line corresponds to a seismic energy density of about 10 to the minus 7 joules per cubic meter. So basically, if the earthquake's big enough or close enough, or both, we should be able to see it with the DAS. This is a diagram that we put together to try and figure out whether or not we were detecting earthquakes homogeneously as a function of position. So before I explain the map, I'll just make the point that the cable that we're using, or if you just take a short segment of the cable, it might be 10 meters long, and it's sort of, let's say it's elongated in this direction. It's only sensitive to vibrations in this direction. It's not sensitive to vibrations across it or up and down. And so you'd expect a long cable to really only be very good at recording earthquakes, which are sending waves or causing shaking in this direction. But what we found in the case of comparing our analysis with SALSA near Haast is that, and I should say blue again represents the DAS calculations where an earthquake was. Red indicates what SALSA obtained. The red dots are much better located. The blue dots are sort of a byproduct of some of the analysis, and they can be improved, and we do the matching based only on time. But the point is, these are the locations of events that we've been able to detect in both catalogues. And if you look at the distribution of azimuths from the fibre system to those earthquakes, and those are plotted in the top right-hand side, you find that the distribution of azimuths for the SALSA catalogue as a whole, many, many times larger record of earthquakes, has the same pattern of azimuths as those events we detect in the DAS system. That was a really convoluted way of saying that the DAS system appears to be recording earthquakes with the same degree of azimuthal reliability as the SALSA network. Why is this? Because I just said it's only sensitive to vibrations in a particular direction. Well, the basic explanation of that is that the cable locally is only measuring one direction, but if you take the whole 30 kilometers, it has a lot of curvature in it. There's a lot of kinks, and that means that as a whole unit, the cable is able to detect waves from all sorts of directions. This is another way of showing what we detected. This is a cumulative histogram of seismic energy density for events, earthquakes that we know about from SALSA, but which we were unable to see in the DAS data. That's the gray histogram. And then in red, the cumulative curve for earthquakes in SALSA that we know we detected. And so you can basically see that above a seismic energy density of about 10 to the minus 7 or slightly larger, we start to detect essentially all of the earthquakes. And the logistic regression summary in the bottom right-hand side is another way of saying that. And this is fantastic. This is saying that, again, if the earthquake is big enough or close enough or both, we will see it with the DAS. If it's too small or too far away, we won't, but that's understandable. Another thing we looked at, and I'll just say this very quickly, is that as anyone who's put out seismometers knows, the noise levels vary. They vary on seasonal timescales, they vary on daily timescales due to the wind that gets up in the afternoons, they vary due to anthropogenic problems like people driving up and down the highway, even in Haast. So what we were plotting here is just a very simple analysis showing the number of earthquakes that we detected with the DAS system in blue and the number of earthquakes detected using the SALSA network. And you can see that the hourly counts vary in both cases, but they vary fairly systematically. So even though the DAS cable is embedded only half a metre below the road, it doesn't have any particularly different diurnal sensitivities to recording earthquakes, which is interesting to see. I'm going to skip over that one for the time being. I just wanted to get to this point. I'm not sure if I spoke about this on Thursday, but one of the new uses that we can put this sort of data set to is to study the internal structure of the fault zone in great detail. So here's just a 400-metre sample of the cable. So 400 metres, nevertheless, with the spacing we have means about 101 channels. So we've got 101 geophones in that interval. And an earthquake, in this case about magnitude 3, about 20 kilometres away, has produced those wiggles there. And you can see that these wiggles are the long period, that is low frequency energy is concentrated at a few locations, like here, 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 and here. It's not uniform across this fault zone, and I should have said the red line marks the fault trace, the mapped fault trace. And we can try and model that by taking an idealized model of a fault zone, which might be, to start with, it might be a broad zone of, let's say, 150 meters or so, in which the seismic velocities are uniformly lowered. We can try synthesizing what happens if we send waves through a fault zone like that, and we get a picture which is illustrated in the top right. And you can see that it has some similarities. It's got this sort of low frequency energy confined to a narrow time interval and to a narrow range of channels, but it doesn't have this extended distribution of noise, of signal as we saw in the raw measurements. If we instead just take perhaps the simplest model of a fault, which is a very, very narrow single fault core, and we just propagate waves along that, we can get something a little bit similar, but it's very, very localized. And so what we really have to do is imagine, or at least the suggestion is that we have to imagine the fault here as being a broad zone, maybe of 150 or 200 meters, in which are embedded a series of narrower fault structures. So this is only a single earthquake. This is just one earthquake in one location. There's much more work to be done on this, but you can see that unlike using conventional sensors spaced tens of kilometers apart, if you have instruments this closely spaced, you can start to tease apart the internal structure of the fault. I'll very briefly mention the work that Alan Raudsep has done as part of his master's thesis. These are diagrams prepared for a different purpose, and I just noticed there's a couple of errors. This P and this P should both be S's. But these are slices of data, again, recording earthquakes, and you can see a nice clear P wave and a mislabeled S wave here. And in the S wave arrivals, there is structure. It's also present to some degree in the P wave arrivals. And our interpretation of that structure is that it reflects the near surface velocity structure beneath the Haast river valley. So, you know, I've been talking about using these data to study earthquakes, but we can also use the waves from those to image the substructure, in this case beneath the Haast valley. And that's an interesting new area of application. We're doing it in the middle of nowhere, with all due respect to the people of Haast, but you could do this, for example, in Wellington. You could take the Vodafone cable that goes around the harbour and be mapping subsurface structure around the harbour for the purposes of geotechnical studies, etc. And our Australian colleagues have been doing this in Melbourne, taking the urban fibre network in Melbourne to do the same sort of thing. Different sources of energy, they have a lot more trams and a lot fewer earthquakes, but same basic idea. We have so much station density that we can see things that we wouldn't otherwise. Ignore the left-hand two images here. I just want to pay attention to the right-hand one. This is a calculation of how deep we think, and I'm going outside my area of expertise here, but how deep we think the apparent low velocity structures beneath the Haast Valley are. The green data show the results of analyzing the DAS data set. The red and blue curves here are independent measurements made using more conventional active source seismic techniques. And you can see that we account very well for what's been observed previously, but we're actually able to go further than that because this is only a 10-kilometre stretch for the fibre, and we have 2 or 3 times as much. So we've been able to map these sort of structures along the length of the valley, and that has interesting ramifications for how the advance and retreat of the glaciers have carved out big holes beneath this and other valleys. I'll just skip that for now. I said earlier that we've had a really fascinating collaboration with people at Dortmund in Germany, and I'm just putting this in here to not to so much draw your attention to the results, but to just talk in a sort of philosophical sense about how much fun this has been, because this group in Dortmund are a group of computer scientists, of machine learning specialists, and the really neat thing about them is that they know absolutely nothing about earthquakes or seismic waves. They wouldn't know a P wave if they tripped over it. And so it's been fascinating to work with them because we had a problem. We were recording all this signal that we were interested in with earthquakes and so on in it, but we also had a lot of traffic noise, from our perspective noise, and we wanted to remove the two. We wanted to be able to take 50 terabytes of data, go through it and pull out all the earthquakes and pull out all the traffic noise. And working with people like this was fascinating because they didn't get hung up on the sorts of geophysical or geoscientific detail that I might get worried about. They really treated it as a machine learning problem. Just to explain what we really were trying to do, we were trying to give them some raw data, which is called the original, and we were trying to get them to reconstruct that, having removed all the traffic noise, so that we could look at the earthquakes a bit more carefully. So, that's what they did. The orange and the green boxes are just 2 places that we're focusing on for purposes of illustration. This is what goes in. It's got traffic noise all through it, and this is what comes out. Now, there are some limitations to what's being done here. I won't go into the details, but one really fascinating thing we learned later is that we could take an earthquake, in this case a big earthquake, magnitude 7, recorded in the Kermadec, so much bigger, much further away, in many regards a very different sort of beast. We could give the system the DAS record of that event, and it would pull out, it would remove all the traffic noise, even though it had never seen an earthquake of this sort of form. And so that was cool too. You can see it has left big white streaks across the data here. So in a sense, it's pulled out the traffic, but it's been a bit damaging in the process. But nevertheless, even without having seen this sort of information before, the system was able to improve it. So I didn't even say what the previous experiment was called. It's called SIZZLE, South Island Seismology at the Speed of Light Experiment. We did another one called FIZZLE. I would not have chosen this name if I had been present. I don't know if FIZZLE doesn't mean the same thing in Australia, but the day that this happened and we put this network in and the name was chosen, I was in Wellington Hospital having neutropenic fevers, and I was not in a fit state to contribute to anything. So that's the name of it, but I tend not to use it very often. Anyway, FIZZLE was very analogous to what we did at Haast. Haast is up here. We went down to Milford Sound, and here Chorus again have installed a cable that runs from Townend to Milford Sound, and it's a big cable. Even when all the cruise ships are coming back with all of the pictures that people have taken, there's plenty of dark fibre for us to use. And so we stuck the interrogator at Milford Sound, and we shot backwards over another 30-kilometre stretch through the Homer Tunnel and a bit further. And here we have the same sorts of things. We did the same sort of setup. It's shown in the top right-hand photo. One of the things I haven't mentioned, but when we set the system up, when we start recording, we have to actually go along the entire length of the fibre, walk it, drive it, do it multiple times, and tap on the ground and do other things to very precisely map exactly where the fibre goes. And this might sound a little bit trivial, but it's actually very important because when the fibres are installed, or the cables are installed, the contractors will often coil several hundred metres or 1,000 metres of surplus cable in a little manhole cover so that if they have any problems that they need to come back and fix, they can just draw out new cable. And we need to know about that because otherwise we map distance along the cable into our system, and if we don't know the several kilometres of spooled cable, we'll get everything screwed up. So that's what we do. It looks a bit silly, but we have to do it. Okay, so yep, lots of earthquakes. Fiordland has not just the sort of shallow seismicity that we've been recording near Haast, but lots of deep seismicity. I didn't mention it earlier, but you'll see on many of these diagrams yellow streaks which represent noisy channels. These are often noisy in the Haast case at least because they are bridges, and when the cable comes to a bridge, instead of being buried underground, they just string it underneath the bridge. This thing here, this big yellow one, is actually the Homer Tunnel, and that's because as the cable goes through the tunnel, it's just hanging off the wall, so it's not well coupled. If you drive through there, you can see it just sitting on the side of the wall. But let's set the earthquakes aside for a minute and just make the point that we have other things to record here. In particular, there's lots of avalanche activity. So we set this system up in June last year and recorded for 8 months. And in the spring in particular, there was lots of avalanche activity. And it's not just avalanches that we hear about through the news. These things are recorded in great detail because the Milford Road Alliance, which is a hookup between the Transport Agency and Downer, they work tirelessly to keep this road open. And so they record avalanches that occur naturally, they record the ones that they set off intentionally, and they have all sorts of video coverage and seismic records in some cases, infrasound, et cetera, et cetera. So what we've got happening at the moment, and this is work being led by a former PhD student from this university, Konstantinos Mikhailos, now based in Canberra. He is looking at our records of these avalanches and comparing them with all the other data we have from the roading authorities so that we can use this sort of system for 24/7 monitoring because they can't see avalanches coming down overnight, for example, things like that. So here's a nice avalanche just on the Milford side of the Homer Tunnel. This one was videoed. You know, there's a timestamp from a video camera. We know a lot about how big it was, exactly when it was, how much snow came down, etc. And we can see that sort of record in the DAS data set. So here there was an avalanche which came down at about the 16-kilometre mark. Here's a sort of a broad settling out, which apparently is the powder cloud settling after the avalanche has sort of come to a standstill, and then there's another avalanche here. So Konstantinos is going through all the data, doing a much more systematic comparison of what's been recorded. We see rock falls as well. Here is the imprint of a big rock on the road. We can put a GPS on that, a GPS measurement on that, and figure out exactly where it is, and we see it in the DAS data as shown in the top right-hand figure. I did promise something a bit more macabre. This is a record of traffic on the left-hand side leaving or travelling near Milford Sound in the afternoon, the mid-afternoon in January. And so you can imagine, even if you haven't been to Milford Sound, that the mid to late afternoon in January, people have been to Milford Sound, they've had their lunch, they've had a cruise, they've escaped the tsunami, and now they're just hooning back to Townend. And so all of these upward sloping lines represent cars leaving Milford Sound. And most of them are travelling at high speed. Here are 4 of them travelling in a bunch. Here are 2 or 3. And there are a couple of vehicles going the other way. So this is 1 minute's record. This is exactly the same place, but 1 minute later. And we can see these 4 cars here coming in and impinging on one of these cars heading towards Milford Sound. The 2 cars in front, they're unaffected. They just zoom through. They might have looked in their rear vision mirror and seen something happening, but they were not stopping. These 2, though, hit this vehicle here. And you might be able to see this little crash there. It involves the first of these 2 cars, and the second one then idles. And so you can see the noise from its engine as it's just sitting there idling. So you might think this is pretty useless, but actually from the roading, again, from the roading authority's point of view, this is useful information, albeit in retrospect. They're interested in when exactly the accidents happened, how many cars were involved, what speeds they were traveling at beforehand, et cetera, et cetera. So if we take a zoom of the incident, here are those two cars that I mentioned. Here are the two cars that just escaped. Then there are two cars heading in the same direction. This one and this one heading towards Milford Sound were involved. There was one crash or impact here. There was a second impact here and a third impact. And the accident report involving the two drivers talks about how one of them hit the bridge. So that's one impact, spun off, hit a second car, that's the second impact, and then hit the side of the wall or something. So that's not why I got into this business, but you can sort of see the utility of this sort of system. One problem is that if the roading people say, oh, John, can you find the accident that happened sometime in the middle of the afternoon on Tuesday, we're going through huge volumes of data, so we don't have a method of finding this sort of thing at the moment. Oh, this is sort of interesting because what happens next, the crash happens up here at 24 minutes past 3. There's a whole bunch of other cars leaving, hooning out of Milford Sound, but they can't get through. And so they all basically stop, they keep their engines idling, and they turn from a steep gradient into just a horizontal line. And yeah, so interesting details. If you wanted to be able to monitor the traffic jam, monitor the tailback, that sort of thing, you could look at that. So lots of stuff happening down in the South Island. We've got lots of different projects involving the fizzle data from Milford Sound, the sizzle data from Haast, and also the broader context provided by Salsa. So really cool stuff. And if you find yourself with a need to analyze terabytes and terabytes of data, please come and see me. I just want to finish with where things are right now. As I said at the beginning, we're currently recording across Cook Strait. And for this purpose, we have an interrogator installed just in Miramar, just to the east of the airport. And it's recording a 60-kilometre length of this white cable here, which is operated by One New Zealand, or a subsidiary of One New Zealand. That cable extends all the way down to Kaikoura, but we don't have lasers capable of imaging such a long distance. Also illustrated here is the big sort of lozenge at the top. That's the cable protection zone. That is a zone that's demarcated as being a place you shouldn't go, because that's where the high voltage power lines run from the south to the North Island, vice versa, I guess. There are fibre optic cables installed as part of that infrastructure as well, and they're operated by Transpower. So we basically have two sets of fibres we could use to make records across Cook Strait. The reason we want to do that right now is because starting in the next week or two, there's an active source seismic experiment depicted here in the yellow lines that's being done by the Tangaroa, NIWA's research vessel, and they are shooting seismic lines across Cook Strait for geophysical purposes. We're interested in knowing whether we can detect those shots on the fibre. They're not very big. The Tangaroa's air guns aren't that big, but they do let them off very frequently. So we should be able to stack shots. We should be able to stack channels on the fibre and hopefully record them. That's in anticipation of a much deeper penetrating survey shown here for what it's worth in the red lines. This is being done in the next year or 18 months or so by a German vessel called the Sonne. The Sonne has humongous air guns, and so we'd quite like to record those shots as well. We're using the Tangaroa experiment as basically a way of testing that we know what we're doing in the marine environment, confirming that we can see these sorts of shots, working out how to handle them, et cetera, and then we'll record the Sonne shots in due course. Ideally, at that time, we might have an interrogator running on the Transpower line as well. That's not currently in place, but the more the better. So yeah, these are sort of our goals for the Cook Strait experiment at the moment. First of all, to acquire, to the extent possible, the active source shots from upcoming cruises. We want to look at the utility of these cables for recording earthquakes in Cook Strait, because GeoNet doesn't have offshore seismometers. There are no ocean bottom seismometers installed permanently here, so it's interesting to know whether the cable could be used for that purpose in the way that we're detecting earthquakes down south. We do have some interesting things to do with AI about discriminating different groups' signals of interest. And you could use the ambient noise records and other techniques to study the structures beneath the cables. These cables do go straight across canyons, they go across faults, they move on the seabed. So there's a lot of sort of interest from the cable owners in terms of using the DAS to study those processes. There are some stretch goals. DAS has successfully been used to record whales going backwards and forwards. I think there's some fascinating work to be done given the tidal currents in Cook Strait on the oceanographic side of things. There's the feasibility or the possibility of looking at early warning, earthquake early warning using a fibre in Cook Strait, again based on detecting earthquakes very quickly. There are challenges of parsing the enormous volumes of data very rapidly, but that's something that could be looked at. So that's all happening. That's what their system looks like. This is, as I said, just east of the airport. We also record a lot of planes. And there's an earthquake recorded on the fibre, just to prove that it looks a lot like we see on land. This is a big earthquake, or not a big earthquake, magnitude 4.8, beneath the outer Marlborough Sounds. And it looks totally believable. This is just one channel of data recorded somewhere in the middle of Cook Strait. So just to end then, we are going back in the next few months to the FTP to try and collect a longer record from the cable. This is what it looks like if you drive down the west coast and you see a lonely looking container. Inside that container is equipment that we put there 10 years ago. GeoNet have since installed their equipment in the borehole and at the surface, and so there's lots of signals being recorded there. All GeoNet's power and comms equipment is neatly stored there. We'd like to go back there, attach the Australian interrogator and record data for another few weeks or months, ideally. But there is a problem, and that is that at the DFTP drill site, we don't have mains power. And we could potentially put a generator there, but keeping it running for several weeks or months without getting it nicked is probably a bit of a challenge. And so this is a real stretch goal, but one possibility is that we actually we trench in a cable from the wellhead to the nearest farmhouse and record from here. And that would have several benefits. One, there'd be power. Two, there'd be internet. And three, we'd be recording again across the Alpine Fault as well as down the hole. So it's a possibility, but it's a bit more involved. The last slide also, Jamie and I have just had a project funded in which we're going to use DAS techniques as part of a much larger project to study the subsurface beneath lakes, one Lake Tūtira on the Hikurangi margin and one Rotorua down south. And in this case, we'll be doing a combination of the DAS measurements we've been making before, but using smaller airgun shots or active source shots from a vessel going backwards and forwards. So that's work coming up in the next few months. I just want to close by saying, first of all, there's a conference coming up in about a year's time, a year next week or something. And I think it's going to be really exciting to see what's happened in the last few years. So talk to me if you're dabbling with DAS or want to find out what's happening. And the only other thing to say, I just got the email this morning, so I'm taking the opportunity to put it in, but as many of you know, Jamie and I have been leading the charge on developing a new Master of Natural Hazard Science and Policy degree. This will involve 0 distributed acoustic sensing, but the webpage goes live on Monday. Everything's been approved, and so this new program starts up as of next year. That's all I wanted to say. Thank you very much.